So I want to begin the class today by, well, first let me remind you that we defined Alexandra duals last time. So we said that the Alexandra dual of a simplicial complex delta is another simplicial complex whose faces are the complements of the non-faces of delta. Right? And today I want to tell you several things about the Alexandra dual. And one of the things I want to tell you is this theorem that I stated last time, a theorem due to Hochster, which says that if you want to know the Betti numbers of a Stanley-Reisner ring, I sub delta, then basically what you need to do is understand the topology of the Alexandra dual. Okay. So more concretely, what this says is that all the non-zero Betti numbers look like this. They are beta I sigma, where sigma has to be square free. And then we get an explicit formula saying that this number is the dimension of a homology group of the link in the Alexandra dual of the complement of sigma. Okay? So we already proved a theorem that says this, that these numbers can be computed in terms of the homology of something else, which is the upper Koszul complex, right? And you guys did a bunch of computations with these guys, so you understand them fairly well. And so, as you can imagine, what I want to do is kind of reconcile these two things. And so just a reminder that this consists of those guys tau such that x to the b minus tau is in I. Okay. So I want to say two things. First of all, I want to say why I said that if b is not square free, then this is 0. And second of all, why I said that if b is square free, then I get a formula like this. So first thing, what happens if b is not square free? Okay. And so since it's not square free, let's say that one of the entries, let's say b sub a, is greater than or equal to 2. So that's going to be our square. X sub a to the something greater than or equal to 2. So I want to show you something which is that this has a consequence in the upper Koszul simplicial complex, which is the following. That if we have a face of the simplicial of the upper Koszul simplicial complex, then we can add or subtract this element a, and we'll still be in the Koszul simplicial complex. Okay. So if tau satisfies this defining property, then when you add or subtract a from it, it'll still satisfy it. Okay. So why is this true? Well, this is true because the definition of this is that x to the b minus tau is in I. Right? The definition of this is that x to the b minus tau minus a, and well, the effect of minus a is just dividing by x sub a, right? Let's say that a is not in tau, so that this is, of course, if a is in tau, then this is an empty statement. So it's only interesting if a is not in tau. Okay. So I took out tau, and then I took out a, and I get this. Okay. So if I want to show that these two things are equivalent, I should justify that these two things are equivalent. But the thing is that if you look at the exponent of x sub a here, well, b has an exponent at least 2. Okay. So that means that when we look at x sub a if we look at the power of x sub a, then here it's at least 2. And when we divide by xa, it's at least 1. Which means that these two guys have the same support. It's just that the exponent of a is 1 more here. But since I is square free, then it doesn't really matter if you have an xa or an a squared. That's not going to change whether you belong to the ideal or not. And so that's why these two things are equivalent, because they have the same support. Okay. So this is a combinatorial statement that is implied by not being square free. Okay? But the interesting thing about this is that this also has a topological consequence, because after all, this guy is a simplicial complex, right? And what I'm saying is that if you have a phase that doesn't contain a, then you can add a to it and that'll still be a phase. Okay? So when I draw this simplicial complex, whenever I have a phase, I mean, let's say that a is over here, right? If I have a phase here, let's say, I don't know, BC. Well, maybe I won't add more letters to this. If I have this edge, then I also have the phase with this edge and this vertex, right? So I have this guy. If I have a triangle here, then I must also have the triangle union this vertex, which means that I must have this whole tetrahedron over here. Okay. I don't know, if I have a point here, then I must have this. Which means that this complex looks different from an average complex in that everything goes through A. And we call these things cones because it looks like a cone, right? It's basically you take the rest of the simplicial complex and you take the cone from A to all of it. Okay? This is what the simplicial complex looks like. This is a cone over A. So let's go back to homotopy. Sorry, can you guys tell me of the letters in the English alphabet, one of them that is a cone? You know, so we have the letters in the English alphabet, right? So which one of them looks like a cone? V, for example, is a cone, right? It kind of looks like this. What else is a cone? X is a cone over this point. W is not really a cone because there's not kind of a central point that goes. Anyway, so Y is also a cone. What's the point? The point is that when you guys hopefully did this exercise about homotopy classes, all of these guys have the same homotopy. It's the homotopy of a point. Why? Because remember that homotopies allow you to squish everything into a point continuously. And so the point is that this is homotopy equivalent to just a point A. Remember what that means? I mean, you have to go back and see what that means, but the intuition is just that you can collapse things like this where you cannot collapse as wholes. Okay? But then, what this tells you is that if these guys are homotopy equivalent, they're supposed to have the same homology, right? I stated that. Okay? Now, we're looking for the homology of this guy, but what we're seeing is that it has the same homology of a point, and we know that the point has no homology. Everything is 0 for the point. because it's a cone over A. This is what's called contractible. Contractible precisely means homotopy equivalent to a point. And therefore it has no homology. Which is what I wanted to show, right? I wanted to show that if I'm not square free, then this is exactly beta I b. And it's equal to 0. So I think this is when it starts getting interesting, when you actually start using some topology to prove algebraic things. If you try to prove algebraically that this number is 0, you can do it, but it's a lot harder than seeing that this thing has no homology. Okay, so that's part A. That's why if I'm not square free, then I don't contribute anything to the resolution. My Betti number is 0. Now if B is square free, then I need to justify that the dimension of this guy is the dimension of this guy. Well, that's easy, right? If I write the same thing twice. That's not what I mean. I mean that link, right? And I guess here I've been calling square free guys sigma, so let me call it sigma. Okay. So this is what I would need to show. Now you see these are vector spaces, so saying that the dimension of the vector space is the same thing as saying that these homology groups are isomorphic as vector spaces. Okay? And again, one way that you could do that is to say, well, maybe, these guys are topological objects, and maybe I can show that they have the same homology topologically. Well, it turns out that actually it's easier than that, because these two are exactly the same thing. Which is kind of good news. We don't really have to invoke any topology. We just have to look at the definitions and see that these two things are equal to each other. So this is true because the upper coswool complex with respect to a square free degree is precisely a link in the Alexandra dual. So that's how we prove this, and this is going to be in your next homework to prove this equality. So modulo that you do your homework, then you will have a proof of Hochster's theorem. Okay. It's a great theorem, and it's really one of the first theorems showing all the relationship between all different fields. Okay, so that's that. What I want to spend the rest of the class doing is saying more about Alexandra duals. So here's an application, but this is only one of the reasons that we want to define Alexandra duals. So I want to tell you more things about this. So, for example, one thing that I wanted to mention is that whenever we use the word dual in mathematics, we generally mean some operation that takes an object and assigns to it a dual object, but it's kind of inherent in the word dual that you mean that it goes back and forth. If you take the dual of the dual, then you should get your guy back. And this is something that we I think maybe I wrote this on the forum, but I haven't said it in class. So this is the one of the first things that you want to check if you want to use the word dual. Okay, and you check it, and it's easy. So that's the first thing. Now, what I want to do now is give you two more incarnations of this duality, two more reasons why this duality is a good thing. So, Alexandra duality. The first reason is going to be algebraic, and the second reason is going to be topological. So what does Alexandra duality have to do? I mean, what algebraic consequence does duality have? What properties? Well, the first thing I'll remind you is this, that we define Hilbert series, right? So, and let me talk about the fine Hilbert series. So, if we want a fine Hilbert series, we need this guy to have a fine grading, right? So this is a finely graded module M over a polynomial ring. And then we prove this great theorem of Hilbert that tells us that actually these Hilbert series are much simpler than they seem at first, because they're just a polynomial divided by, they're just a rational function, and a very explicit one. So the numerator is some polynomial that we call the K polynomial. And the denominator, it depends. If you look at the coarsely graded version, it's just 1 minus x to the n. And if you look at the finely graded version, it's the product of the 1 minus xi's. Okay? And we basically said that if you want to measure the size of the module, basically it amounts to computing this K polynomial. So here's a nice theorem. The theorem says, it's called the Alexandra inversion formula. The theorem says that it's kind of the same thing if you want to compute this for the Stanley-Reisner ring of delta or of the dual of delta. So what it says is that if you do this for the Stanley-Reisner ring of delta, to compute this K polynomial, you're basically also computing the one of the dual. Except that you're computing it somewhere different. You're computing it at 1 minus x. Now let me say another thing about this, which is you should remember that computing the K polynomial for I sub delta is equivalent to computing it for S mod I sub delta. Because we said that the Hilbert series of I and R mod I are very closely related to each other. We can get one from the other one. And so really this says that you can do this computation for whichever one is simpler, delta or its dual. And if you have one, you're going to be able to get the other one. And this can really simplify your work sometimes. And you can see that it makes sense that this simplifies your work, because in in the one example that we did explicitly of Alexander duality, we have two simplicial complexes that are dual to each other, and one really looks a lot simpler than the other one. One is, you know, one triangle and an empty triangle, whereas the other one had a hollow tetrahedron and it had all these other things. And that second one is harder to compute than the first one. It's messier, but this tells you actually it doesn't really matter which one you compute. So you would go for the easy one. Okay. So to prove this, you have to go back and see something that we proved back when we proved this theorem. We did this very explicitly. We found a formula, and the formula said this. You sum over the faces of your simplicial complex product over the faces of xi, and, sorry, product over the things in the face, xi, and the things not in the face, 1 minus xt. So we proved this formula. So that's the left-hand side. And what about the right-hand side? Well, let's write out explicitly what the instead of the k polynomial, let me actually just compute the Hilbert series. So this is a monomial ideal, right? And so by computing the Hilbert series, what I want to do is just tell you in multi-degree B, how many things do I have? And that's going to be either 1 or 0, according to whether x to the b lives here or not. And so what I'm going to get is basically the sum of the monomials, monic monomials, in here. Now, let's say, let me just write it like this. Sum of the monomials in here. But maybe I should put a b here so that it doesn't look to you like this is square free, right? Because you're supposed to do it for every b. Now, when do you get to be here? Well, you get to be here when you're a multiple of one of the generators, right? This is a monomial ideal. Now, so this is true if and only if this is a multiple of one of the generators. Now, the generators here are square free. And so to be a multiple of a square free thing, what should happen is that your support should contain the support of that thing. Okay? So x to the b is in here if and only if its support contains the support of one of the generators. And the generators are exactly those things over there, right? Sorry, I'm saying something backwards because remember this is the Stanley-Reisner ring, the Stanley-Reisner ideal. And so the generators of the Stanley-Reisner ideal are the non-faces, not the faces. Okay? And so here I'm looking at the support of the non-faces. And what I wrote is the faces, right? You get to be a face if you look like tau bar, where tau is not in delta. So you're not a face if your tau bar with tau in delta. Okay. These are the non-faces of the Alexandra dual. Okay. So then what I need to do is basically look at, for each one of these guys, I'm going to sum all the monomials with support so I'm going to sum all the monomials such that the support of B is exactly tau bar. That's what I get. So I take all of these guys and I classify them according to their support, but their support should be one of these guys. And then it's just a matter of computing, because remember that this kind of looks like a bunch of geometric series, right? So basically what you need to do is, for each element of tau bar, you need to choose your exponent. And the way you do that is, for each element of tau bar, which I used, I choose, well, am I going to be contributing an xj or an xj squared? What am I going to contribute? But it should be some contribution that is not 1, so that j is in the support. Okay. And so what I get is the product. Now instead of j being in tau bar, let me write j is not in tau. And this is just xj over 1 minus xj. Okay. Then I put common denominator. And so the common denominator is the product of all of the xj's. And what I'm going to get is this times this. If you see this, when I compute this, then all of the terms in tau are going to cancel all of the terms in tau here. And for each term not in tau, I'm going to get xj over 1 minus xj. Okay. So I do this quickly because this is almost the same computation we did earlier to prove this. Okay. Actually, this is exactly the same computation, except now we're doing it for delta star. Where am I going with this? The thing is that I have a theorem about the k polynomial, and I'm computing the Hilbert series. And what I found is that the Hilbert series is something over the denominator that I expect. Right? Which means that this big thing that I have over here is the k polynomial of I delta star evaluated at x. And the thing that I would like you to do is now look at this expression and look at this expression. Okay? And maybe I should stand in the middle of the two, and hopefully the camera will point to the right place. So here we're summing over sigmas. Here we're summing over tau. So just pretend that sigma here is tau here. Man, the camera's pointing to like the other board. I don't know what it's doing. Now, here we're taking the product over the i's that are in my face of 1 minus xi. And here for the i's that are in my face, I get xi. And here for the j's that are not in my face, I get xj, whereas here I put 1 minus xj. And so basically, these two formulas look exactly the same, except that where you see x here, you should put 1 minus x there. Okay? And that's precisely what I'm asking you to do is take this formula for k, but instead of plugging in the variables xi, plug in the variables 1 minus xi. So when you do that, here, you're going to get this same thing. Okay? So that's a proof. Just kind of carefully go through the motions of computing these things. But the fact is what's more important. That basically the growth of delta and of delta star are the same. The Hilbert series are, if you have one, you have the other one. Okay? So that's the algebraic advantage of Alexander duals. Okay? Now, I think I need just about everything that I have on the board. We go back here and now talk about Alexander duality and topology. Now, again, what's the story? The story is basically that Alexander was a topologist, not an algebraist or a combinatorialist. And actually, if you look up at Alexander duality on Wikipedia, you're going to get to a topology page before you get to a combinatorics page or to an algebra page. So just to give you a general idea of what this says, let me write out a theorem, which is what is usually called Alexander duality theorem. And what we're going to spend the rest of the class doing is kind of unraveling what this means. So theorem, and it's called Alexander duality. Let's say in topology. It says the following. If you have some topological space inside a sphere, okay, then the topology of A and the topology of the complement of A are very closely related. So topology of A is very closely related to the topology of the complement of A. And let me just say here, under mild hypothesis. So this is true for any kind of reasonable space that lives in Sn. By reasonable, I mean that anything you'll encounter will have this property. But if you go really hard looking for a counterexample, then there exists. But in nature, this is true. Let's say it that way. Okay. So why do we need 20 minutes to unravel this? I just wrote it. Is there something here that looks unfamiliar? So this is for all k. Right? There's only one subtlety here, which is that our subscript moved up. Other than that, you understand everything in this statement, except that the subscript moved up. And that's not a typo. So I'll tell you what the story with that is. The story with that is that, so go back to when I first started discussing algebraic topology with you, and I told you that if you have a topological space, you want to associate some algebraic object that stores information about the space. So we've been talking a lot about homology groups, and hopefully we like them a lot by now because we see that they're an algebraic tool that finds topological things. It finds holes, for example. Okay. So that's homology theory. But that's only one of the many theories in algebraic topology, and another one of the theories is a cohomology theory. Okay. And so that's what I will explain to you. And the thing is that this is homology, and this is cohomology. So once I explain to you what cohomology means, then what this says is the kth cohomology of A is the n minus k minus 1 homology of the complement. This is homology, and this is something called cohomology, which is very similar, as you can imagine, because the name is so similar. By the way, you guys might know that when we have duality theories, we like to use the word co. So if you can ask Amanda, her whole thesis is about co something, and co something means the dual of something often. Okay? And in a very precise sense, these theories are dual to each other, and so in that sense, it makes sense that Alexander duality should translate to a topological duality. So this is one version of the theorem. Now I want to give you, let's say, a more combinatorial version of this theorem, but also topological. So this is maybe a more combinatorial version. And it says that if you have a simplicial complex of dimension n minus 1, then the same statement is true. Actually, let me not even change the, let me make it look exactly like this. And all you have to do is put the dual here. Okay. So again, I'll tell you what cohomology means, but this tells you that the cohomology of a simplicial complex is exactly, it's isomorphic to the homology of its Alexander dual. And so in that precise sense, their topologies are really closely related. A consequence of this is that we can write an alternative formulation here, because here I'm computing homologies in the Alexander dual, and what this allows me to do is to turn that around and turn the dual into the one that I care about, which is delta, but I have to change the theory to the dual theory of cohomology. And so what I get is this. Now, the other nice thing is that instead of getting links, what I get is I get the simplicial complex and I get its restriction to sigma. Okay? And restriction is more intuitive. So for example, if delta looks like this, forget. What did I call the vertices? A. This is B? B. This is C. A. D. E. And what's the restriction to, I don't know, A, B, D? This is a lot clearer than links. The restriction is just forget about the other guys and just see what happens when you only look at A and B and D. So this is a lot easier to spot. You just erase all the faces that involve other stuff, and you restrict your attention only to the ones involving the variables that you care about. So if you look at this formulation, this is a really, really clean formulation. It says the Betti numbers of the simplicial complex delta in degree sigma are exactly given by the cohomologies of the simplicial complex delta restricted to sigma. No need to do a full complex, no need to do a Alexandra dual. This is really very explicit. Okay? And this is actually Hochster's theorem, and people call this the dual Hochster's theorem. They're equivalent to each other. Okay? So I also think that if you've never seen cohomology, then maybe this serves as a good reason to see it. So what is cohomology? Let's see. I have 10 minutes, so let me see what the best way to say this is. Okay. So cohomology looks like this. You start with a simplicial complex delta. Okay. And now for homology we took something called the chain complex. Okay. Now we're going to do something called the co-chain complex. And because I only have 10 minutes, I'm going to sweep some details under the rug that are not really important. So the co-chain complex is going to look basically like the chain complex, but backwards. What I mean by that is that you start with the one-dimensional things, then you go to the zero-dimensional things, then you go to the one-dimensional things, and you continue all the way until the biggest dimension that you have. So it looks like this, where you guys already know what each one of these things is. Okay? This is a vector space with a basis given by the one-dimensional basis of delta. Now, one of the little annoying details is you need to put little stars here, which only mean that these are kind of the dual objects to the ones we had before, but they're the same. They're not the same, but they're equivalent, let's say. If you guys are familiar with vector spaces and dual vector spaces, it's exactly that. This is the dual vector space of the one we had before. But the thing is that a vector space and its dual are isomorphic, and so that's why we can more or less think of them as the same. Now, the other thing I should tell you is that when you have two vector spaces and a homomorphism between them, a linear map, then that means that you also have a reverse map. So this gives you a reverse map where you put the dual spaces here, and the reverse map is called the dual map. Okay. And again, these guys are isomorphic to each other, and these guys are isomorphic to each other. And so effectively what this is doing is reversing your arrows. Okay? And there's a rule for doing this. Our chain complex looked like it was going in this direction, right? We mapped the boundary of n minus 1 was n minus 2, the boundary of n minus 2 was n minus 3, etc. And we're kind of using this very general gadget to reverse the maps. Okay? And so, for example, we used to have a map from here to here called the boundary map n minus 1, right? Okay. Well, that was going in that direction, so if I want to reverse it, I need the dual of that map. So that's what I do. And I'll tell you what these maps are. Okay. So what is... Sorry, so the convention actually is a little bit different here. So what people like to do is just put in a superscript instead of a subscript here. So but really, you should think that this is just the dual of this alt map. And what you do is something very similar to what we did before. Maybe what I'll do is just an example. I think that'll be clearer than. Well, maybe I'll just write it like this. Okay. So I need to define my map delta I, and this should be a map that takes an I-dimensional phase. No, you see, delta 1 takes a 0-dimensional phase and makes it into a 1-dimensional phase. So here I should take an I minus 1-dimensional phase and make it into an I-dimensional phase. Oh, a sum of I-dimensional phases. And the way you do that is, remember that what we did before? To take the boundary map, we took a phase and then we took each vertex out one at a time. So the boundary of ABC was take away A, you get BC. Take away B, you get AC. Take away C, you get AB. Now we're going to do exactly the opposite. We need to add one dimension. So what I'm going to do is just add every single guy that I can possibly add. So I add all the guys that I can, which are the guys that are not already in there. And then, just as I remember that I needed some signs to make this work in homology, and here I need some signs also, and so I just put the right sign. Okay, you have to think a little bit about what the right sign to put is here, but it turns out that it's -1 to the position of J in sigma union J. Some sign. Okay. Now, what's the point of all of this? The point is that we have the same properties that we had before. This really is a complex in that if you compose two of these maps, you get 0. So here's some facts. If you compose this map and this map, you get 0. And again, what this means is that the image of delta I plus 1 is inside the kernel of delta I. And this would be exact if this is equal. And we basically want to measure the inexactness of this thing, and that's the cohomology. Okay. Did I do something wrong?
Delta 0 maps to where delta
Yeah.
1 maps from.
Yeah, that's right.
So you should be composing from the other direction. For
this is right and this is right. No?
Wait, if you start in the first guy and you map it
No.
to
This is like
yeah,
this.
then you map to the next one. Okay. So that's
Yeah. And so I define cohomology to be the inexactness of this thing. Okay. So the kernel of delta I plus 1 mod the image of delta I. So you see it's a theory that looks very much like homology theory. I know probably right now you're a little bit overwhelmed by this definition, but remember you also were when I defined homology, right? And it's equally overwhelming and equally simple in a way. So the point again is that this also captures some of the topological properties of delta. Okay. And so depending on what you're trying to do, sometimes you want to use homology, sometimes you want to use cohomology. And if you look at the structure of this theorem, it actually seems like it is more natural to use cohomology, because the formulation is cleaner in that term. So that's it. So you kind of have to play with some examples to figure out what this cohomology is. Now, one thing I should tell you is that actually, I think I forgot to put some stars, by the way. But one thing I should tell you is that we've been working over a field. Remember that I told you you can do homology over a field or over an abelian group. We've been doing everything over a field, and actually over a field, homology and cohomology are equal to each other. They're isomorphic. Okay? So in a sense, if you don't like this too much, then because we're working over a field, there's always a isomorphism between the ith homology and the ith cohomology. And so you might as well, if you're happy with only working over a field, you can move the exponent up and down, whether you prefer homology or cohomology. But when you change to an abelian group, this changes. Okay? And this is important because this theorem, the classical theorem of Alexandra, really you do need cohomology here and you do need homology here if you're going to work with an abelian group. Okay. One thing that I'd like you to think about is what's the relationship between these two guys, because I'm kind of claiming that they're more or less the same theorem. I should tell you that the mild hypothesis is just that you can triangulate A. In other words, you can represent A by a simplicial complex. Okay, so you should think about why it is that these two are kind of incarnations of the same thing. Okay. So I think this is all I wanted to say about this. I did write a little bit about duality of vector spaces in the notes, and you should look at this, all this stuff about the